In this class, we study separation of variables. The classical mechanics has the equation of motion that is F equals ma. And usually F is the gradient minus the gradient of potential energy if the force is conservative. And acceleration is the second order time derivative. So equation of motion is second order derivative of displacement and potential energy is a function of x. This is general form. For example, we have a spring mass system. Its potential energy is 1/2 kx squared and the corresponding force is a minus kx. So negative value of x derivative is this. And in that case, mx double dot plus kx equals 0. This kind of equation is called differential equation in mathematics. And the origin of differential equation you mostly learn from mathematics class is the equation of motion. So calculus as well as the differential equation was created by physics that is called classical mechanics. The origin is physics, not mathematics. So we are interested in solving this equation of motion. In mathematical world, it is second order linear differential equation. But before we attack this problem, we consider a simpler problem that is a first order differential equation. The most general form of the first order differential equation is the derivative of y is a function of x and y. Most complicated case. But in most cases, what we are considering in the physics problem, in reality, they are quite common. The simplest case is a factorized form. It is not mixed up, but factorized as a product of function of x and function of y. In that case, the right-hand side is replaced with this one, and we say this equation is called variable separable. X and y are factorized, and only differential of x is on one side, and only the differential of y is placed on the other side. Okay, if I substitute this, then what I get is raise. What I get is dy over dx equals ax by. We multiply dx over dy to both sides. So dx cancels, so we have dy over by, and right hand side by cancels and ax dx survives. Left hand side is only a function of y, and right hand side is only a function of x. We have separated the variables x and y as it is. In that case, we can integrate both sides simultaneously without any problem. If you know an integral table, you can integrate this. If you know the integral table for this, you can finish the integral for the right hand side and let them be equal. For example, y equals a function of x. Okay, they are correlated. So If I substitute x1, then you will obtain y1. If I substitute x2, then you will obtain y2. So the integral of this should be carried out in the interval x1 to x2, but at the same time, if I have x1 on the right side, and it must have y1 on the left hand side, and they should match together. So what I have done is do the integral from y1 to y2 and x1 to x2, and these two are correlated by the explicit function of y. But I do not know what the function is yet. Only if I solve this equation, I can determine the x dependence of y completely. By the way, I would say this is an initial condition. Initial condition means y of x1 is fixed to be y1. So, and then I'd like to vary x and y arbitrarily, provided that we have a function, consistent functional dependence on x. Okay, let us apply this method of this variable separation of variables. We can compute this kind of equation of motion. What's that? We have a particle moving under constant gravitational force along this direction. I have chosen x is positive relative to the initial position. So this equation indicates that equals minus bx dot plus g, and g is the direction of increasing x, and then we have additional force. Aha, there is missing. I have to multiply m in here. mg is the weight gravitational force applied to the particle of mass m. So this should be mg. And then we have another force that is proportional to the velocity. So it is accelerating due to the gravitational force, and as the velocity increases, b is a positive constant that is called the damping coefficient. If there is a damping force that is linearly proportional to the velocity, but the sign is negative, that means it is opposite to the velocity. X dot is going down along the positive x-axis, but x dot minus x dot is opposite to the velocity. So there is a damping force opposite to the velocity of the particle. So we'd like to solve this equation of motion. And it looks like the second order differential equation for x. However, I find this is a second order derivative of x, but that is a first order derivative of velocity. And x dot is the velocity itself. As a result, this equation is linear, the first order linear differential equation for velocity. So let us solve this equation in terms of velocity first. So I copy this one, x double dot is the time derivative of velocity. Bx dot is replaced with bb, and mg is copied as mg. How can I separate the variables? Move this guy to the right hand side, then I would get this one. So m dv over dt equals minus bv plus mg. Okay, and this one is function of v only, time dependence appears in the denominator only. So exchange these two guys. Then I would get dv, dv divided minus bv plus mg equals the dt, something like that. So why don't we multiply minus b over m both the sides, then it becomes this, and left hand side this factor is removed and this part is modified by this one. By the way, wait a second, mg and minus bv, and we pull this out, b factored out, and becomes mg over b. Okay, that's fine. So we can see this left hand side depends on v only, and right hand side depends only on t. So we have separated the two variables of v and t. And now we can integrate both sides simultaneously. This integral, I know the integral table, this is log, but these and these are different, so I change the variable by subtracting this, but that doesn't change anything. But if I change the variable from v to v minus mg over b, then the upper limit and lower limit are shifted by the same amount. Okay, and then right hand side, the integral is from 0 to t. So left hand side, the integral is over v minus mg over b, but evaluate it at t equals 0 and evaluate it at t in general t. We carry out the integration, that is a log. Subtraction of the upper limit value and lower limit value is just the ratio of the argument. And this integral is trivial, t minus 0, that is identical to t. We know log is the inverse function of exponential, therefore it is completely expressed in terms of this exponential. And then multiply this factor both sides, we obtain this. And move this guy to the right hand side, we can determine the velocity at t. We can see as t goes to infinity, exponential factor decays to 0. So this one disappears, and as t goes to infinity, we can see the velocity of a particle reaches a constant that is called the terminal velocity. Because we have obtained the velocity, we can integrate this velocity one more time to obtain the position of particle at any time. So that can be done by substituting this explicit time-dependent function of v into this integral. We find that explicit evaluation of integral is constant. So from 0 to t, this one becomes a t, and this one is minus b over m exponential b over mt, and evaluated t, and evaluated t equals 0. So the value is this one gives this and 1 minus exponential factor. Again, as t goes to infinity, it has the contribution, this exponential contribution disappears. When t is very small, when t is very small, we can expand this one in powers of t by expanding e to the minus x equals in 1 minus x plus x squared and so on. Using this expansion formula, we can obtain the position of the particle when t is small enough. The same method can be applied to the solution to find the solution of RC circuit. In a similar manner, we can separate the variables, Q-dependent part and time-dependent part, and the logic of finding solution is identical to what we have seen in here. And finally, we can reach the point the charge of the Q saved inside the capacitor can be determined like that.